This is a binomial. It has two parts to it, two terms that have been added. In this example, we're going to see quite a lot. It's a and b, but really those terms could be anything. The issue is really that multiplying these binomials and squaring them, cubing them, putting them to higher powers is tricky. It's a long process that can only get longer the more brackets and the more binomials you're multiplying. Some of you will be able to tackle these double and triple bracket problems on the screen, but with 5, 10, maybe 20 brackets, the methods we use take too long. Now, just as an example, for double brackets, some of you may use the FOIL method, first, outer, inner, last, where you make pairs, multiplying terms together, and then simplifying for an answer at the end. But this doesn't work for more brackets. It doesn't generalize. What we want is a formula, something that takes us straight to the answer for any power of any binomial. And when we want a formula, we need to find patterns. Now, to look for these patterns that we need to be able to generate a formula, we're going to need some examples to look at. So for now, we're going to write out the expansions for powers up to 5. Now, we could do this one by one, expanding bracket by bracket. It would take a long time, but we'd be able to get the results you see now. Now, it's tricky to see patterns in this mess of numbers and terms, so we're just going to look at one of these examples. A plus b to the power 4. See if we can spot anything interesting. Now, the numbers here in the middle, these coefficients 4, 6, 4, they turn out to be the trickiest part of this formula. So we'll come back to them later. Look, just for now, at the powers of a and b, and we can see something interesting. The powers of a start at a to the 4 and decrease, walking down one by one, until we get to no a in the last term. And the b's, they do the opposite. They walk up from no b to b to the 1, b squared, b cubed, b to the 4. Now that's a pattern, that's a trend, and if we look further we can see something else interesting. Grey everything out except these powers, and you'll see they always add to 4. 4, which was our original power. That seems to be the maximum power for all of these terms. And that's a pattern that doesn't just work for this example, it works for every example. A plus b to the n starts with a to the n, our maximum, and then walks its way down to a to the 1, a to the 0, on and on. B does the opposite, starts at b to the 0, and then walks its way up to b to the n. And as you'll see, all the pairs of numbers here add to n like they did before. The only mystery that we have left, the numbers, the coefficients. But luckily enough, that's something that we can solve just by looking at things from a slightly different angle. Now, this new angle that we're going to be using is going to involve a piece of maths called combinatorics. And this lets us study how to choose and arrange and combine different objects. To see how this works for us, let's go back to our simplest example, which was a double bracket. Now, whether you use FOIL or not, we know how to do this. We know that you make pairs, picking out one term from each bracket, multiplying them, and repeating, until you've covered all the pairs you need to make, the ones that FOIL teaches you to make, first, outer, inner, last. And then, at the end, once you've made all your pairs, we add them all together, and simplify where we can, to make our final answer. Now, hopefully you can see where maths of choosing and combining is going to come in here, while we do another example, this time with a plus b squared. Now the two a's, they times together make a squared. The next pair we can make is a, b. They times together, they make ab. Another pair we can make now is b, a. Now they have the same product, ab, but it's a different way of making that product. It still counts, it's still valid. And then at the end we have b squared. When we add them all together and we combine the middle terms, simplifying, we see the 2, the coefficient, come up where we hadn't seen it before. Now we know now that this just comes from the fact that there are two different ways to make our AB term. Let's do another example to make sure. Now in this example we're going to be using 3 brackets. So instead of pairs we're going to make triplets of terms. Now our first triplet, AAA, makes A cubed. AAB makes A squared B. But again, that's not the only way of getting to that grouping. I'm showing you a couple of other ways to make that same product. ABB makes AB squared, but again, there's different ways that you can make that same mixture by just picking out your terms in a different way. And our last triplet, BBB, multiplies to make B cubed, and that goes at the end. Now we will see the first and last terms never have a number in front, because there's only one way of making them, take all the A's from all the brackets. That's not true for the terms in the middle though. That 3 shows that there are 3 different valid ways to get to that specific mixture of A's and B's. Now, this method is completely valid, it follows the same rules as before. We just have a better idea of what these coefficients mean now. So we've gone from this tricky algebra problem about coefficients and expansions, and we've transformed it, rephrased it into this simpler problem, talking about the ways of making these mixtures, these combinations of A's and B's, using our plucking out method. Now this question can be made simpler still by realizing that we don't need to talk about both the A's and the B's. Now if instead of saying we pick out an A from this bracket, we just said we leave it blank, it doesn't make a difference to the maths of how many combinations there are. And plus, we always have the total, so we can work out one from the other. Really, it's just a bit of extra information, so we'll choose to get rid of talking about the A's to make a simpler problem. Now, of course, it doesn't just work in this one case. If we swap the numbers around a bit, say we're looking for this term in the expansion with 5 brackets, well then we can change our question at the bottom accordingly. The number of B's is now 2 because it's a B squared term, and the number of containers, the brackets, is now 5. So we're going to generalize. Again, if you look up in the top right, we're going to say the power is n. We're going to say the number of B's is now r. That's sort of a convention in combinatorics to use r. So first of all, we got to realize that the power of A is just n minus r, the total take away the B's. And then we can change our question down at the bottom. Say that the containers is now n, the number of brackets, and the number of B's is r, because that's the power of B. Luckily enough, this problem is so common in combinatorics that it has its own notation and its own name. It looks like this. It's pronounced n choose r. And what it gives you, if you plug in the right n for the containers and r for the objects, is the number of different ways of picking them out. That's exactly what we want. Now on your calculator it looks more like this. It has a different notation, but it does the same thing. What we really want to see though is how this plays with our formula from earlier. Now this was one of our examples, a plus b to the 5, except now we can replace all of these coefficient question marks with our n choose r terms. Now we have to figure out what to put in. For all of these we're going to be picking out of 5 brackets, so n is always going to be 5. R is a bit trickier, but r is just the number of b's, right? So we just have to match r to the power of b in that term. It's going to be different for every term, but it'll work. Now for our general case, it's going to be really similar. We're going to do our same thing of the a's walking down and the power of b walking up with our n choose whatever terms in front. This is going to be our general case with the power of b just being r, and the lower part of our choose function also matching being r. And that's going to happen, walking all the way up until b to the n at the end. So now really we have a working formula, or the only mystery left is this choose function. Now I'm showing you on screen how to work it out, but to really understand this, we're going to have to go through factorials, and they're really quite simple. N factorial is just all the numbers up to n multiplied together. Simple as that. So 5 factorial, 5 times 4 times 3 times 2 times 1. Easy. But the really interesting thing here is the link to combinatorics. So say we have 3 numbers, 1, 2, 3, and we can put them in a different order. What we want to know as a combinatorialist is how many ways can we do this? How many ways can we rearrange these numbers and get a different order out of it? What helps is to think of 3 spaces we can fill up with our numbers to make an arrangement, because that lets us take things one by one. Let's look just at this first space. Well, we can put any of our 3 numbers in there, so we get 3 choices. We start off with a wide range of different options. Our second space, well, one of those options has been taken up. It's gone in the first space already. There are 2 left, 2 choices. And whatever's left over, whatever hasn't been picked, just goes in the third space. One last choice left. To work out our total, just think. There are 3 initial choices we can make, and each of those has 2 options. What we get is 3 times 2 times 1. That's 3 factorial. That's the number of ways of arranging them. And of course, this doesn't just work for 3, it works for any number. N factorial, in general, is the number of ways of arranging n objects. That's the important link to combinatorics. Okay, so we know about factorials, we know how to do them, and we know how they link to rearranging items. But that wasn't our question. Our question was similar, but we were choosing things, picking them out from a list of containers. So let's focus back on that original question. We'll do an example here, and the example is 3 B's that we're going to choose from a list of 5 brackets, just some example numbers. Now, what helped us last time with our factorials was taking things one by one, not doing the whole question at once, but doing it step by step. So let's look just at B1, our first B. Where are we going to take this from? Well, really, we have 5 choices here, 5 brackets. Any of them could be where we take our first B from. B2, it's slightly different. B2, one of them has been taken up already. We've chosen one of our items. We can't use it again. We only have 4 choices left. Same logic for B3. There are 3 brackets remaining that haven't been used up, so we have 3 more choices. Now, using the same logic as before, multiplying up our choices gives us our total. 5 times 4 times 3. That's the number of ways of doing this, picking 3 B's from these 5 brackets. So what we're left with is this kind of incomplete factorial, one that stops after 3 terms instead of going down to 1. Now, we don't want to write this out in full every time, we still want to use factorials to make this simpler somehow. So we just have to realize that our answer is this full 5 factorial with this tail of 2 factorial, 2 times 1, chopped off at the end. So we can just write it as equal to this full 5 factorial divided by 2 factorial. This cancels out all the terms we don't want. And so we can generalize now, we can translate back into n's and r's. This 5 up top just comes from n being 5, our number of brackets, so we can translate that. 2's a bit trickier, but we just have to realize that it comes from what's left over after we take our 3 b's from our 5 total brackets. It's 5 minus 3, which translates into n minus r. Now, this isn't mathematically rigorous, but it helps get an intuition. And now it looks like we have a formula for n choose r, what we've wanted all along. Now, actually, there's a small mistake hidden in here. I'm not surprised if you haven't spotted it. But it's not that tricky to correct, so let's go through it. Now, this mistake was actually unavoidable because it came from the thing we used to make our problems simpler, which was giving things an order. Now, this was our first example when we were making triplets, when we first came up with the idea of making combinations. And you'll notice that there's nothing labelled 1, 2, or 3. There's no concept of what term is picked out first or second. It's all just picked out at once and added to the running total. So that's a discrepancy between our system and what we should be aiming for. And as soon as we introduce order into systems, it can change things. take a look at this one combination. Now really, this should count as one valid way of making 3 b's, and then we should move on. But with order, what we can do is just swap some terms around, make it seem like a new combination, make it be counted as one, when really it shouldn't be. We've created a flawed system here, and we're overcounting actually by quite a lot, because for every one valid combination, there are 3 factorial ways of rearranging it, repackaging it. That's why we looked at how to rearrange and repackage things earlier. So really, to account for this overcounting, where we're adding 3 factorial things whenever we should be adding 1, we just have to divide our old flawed formula by 3 factorial. This accounts for our overcounting. Now translating back into n's and r's, 3 is just the number of b's. 3 is there because r is 3. Move that down to the denominator, and there it is. That's a complete, valid formula for n choose r, and it's one that we can now use in our full binomial theorem. And this is a formula that we've created from scratch by looking at whatever patterns we can find, by creating new and powerful intuitions based on whatever methods we know, and by using links to other areas that we didn't even know were related to help make our problem easier. Because maths isn't about memorizing old solutions to old problems. It's about finding new ones in whatever creative ways we can. Thanks for watching.